In January 2009, the first broadly available and viable cryptocurrency was created. Called Bitcoin, this new form of money was born on the internet. Powering the magic of Bitcoin was a novel underlying technology that would itself become a breakout hit. A digital ledger mechanism that will be referred to as blockchain demonstrated enormous potential in how it authorized, validated, and stored transactions on a computer network. No longer tethered to human oversight, blockchain introduced the notion of transactional trust through computer code. This was a game changer. While it's just over a decade since blockchain technology first arrived, its full potential is still to be realized. Now, all types of organizations are discovering and embracing its value and unleashing its capacity for innovation. The unique qualities of blockchain make it a truly 21st century disruptor that must be understood. Hi, I'm Dr. Jonathan Reinkentel. By completing this course, you will understand what blockchain technology is, how it works, and the ways it's creating new value for different industries. I'll also discuss some of the challenges and risks ahead, where the technology may be headed, and some possible next steps for you or your organization. In this course, I'll keep focused on the big picture and explain important concepts in a way that everyone can understand. If you're ready to explore one of the hottest technologies today, come on, let's jump in and get started. While recognizing that we have 40% of the world's population still to connect, whatever way you look at it, the internet is amazing. It continues to evolve the way we live, work, learn, and play, and with no sign of slowing down. It has significantly impacted industries like media and entertainment and brick and mortar retail. And it's reinvented others like how we manage our money and book travel. And for many, it has changed how and where we now work. The internet has been a big deal, and it continues to be. In fact, the most disruptive days of the internet are likely still ahead of us. Some analysts, including me, will argue quite convincingly that we're still in the opening act of internet innovation. Of course, it's easy to focus on all the positives of the internet. For example, it has created low-cost communications across much of the world, lowered the barriers to setting up and running a global online business, and it's providing new ways to access healthcare information and services. But we're kidding ourselves if we don't recognize that this vast network of networks has some stubborn problems associated with it. Beyond some of the obvious, such as online fraud, misinformation, outages, and hacking, the internet often struggles with the fundamental challenges of trust. This can't be overstated. The history of humanity and much of its success has relied on models of trust. With the internet, we confront challenges such as knowing whether the person you are doing business with online really is who they say they are, or determining if an online service is real, or if private information being shared will be kept confidential. I'm sure you can think of many other trust issues like these. Despite these challenges, we've done wonders reducing risk and building trust with existing technology. More of us are using stronger passwords, multi-factor authentication, and biometrics such as our fingerprints and faces to gain access to systems. We have security technologies such as firewalls, intrusion detection systems, digital certificates, and CAPTCHAs, those quirky requests that require us to prove we're human by identifying text or objects in an image. Something bots still can't do, at least not yet. With these mechanisms and others for security and trust, we've come a long way, and yet issues persist. For example, business systems and databases continue to be compromised, made unavailable, and money, information, and identities are stolen. Without more rigorous online tools to increase trust and reduce risk, innovation will be impacted, and at worst, held back from meaningful progress. If we want ironclad, convenient online voting that people will trust and use, workable long-term digital currencies, self-driving cars that securely negotiate with each other, improved and seamless methods to authenticate identity, and more, we're going to need a more secure and trustworthy internet. Security innovation continues to move at a frenetic pace. Fortunately, new ideas are emerging all the time, sometimes in surprising ways. That's what happened with the introduction of Bitcoin. The solution that has enabled the success of Bitcoin and almost all the cryptocurrencies that have followed is fundamentally a novel security and trust mechanism. That technology? Well, that would be the distributed ledger, or blockchain, as we now refer to it. What blockchain technology achieved was the notion of trustless architecture. Put another way, trust will be a feature of software code and not that of human intervention. It's a big idea, and it works. While blockchain enables cryptocurrency to function in a trust manner, this core quality has made it valuable in a large number of contexts. In fact, in the next chapter of internet innovation, we may have blockchain to thank for opening some new doors. In order to grasp the fundamentals of how blockchain technology works, we first need to cover the basics of a database in a client-server environment. If you already know what a traditional relational database is and how it works, you might consider skipping this video. However, I think everyone might enjoy a brief primer on the topic. Fundamentally, a database is software where we store and manage files and records on a computer system. We can store these items, I'll refer to them simply as data from now on, in a structured way or an unstructured way. Let's first look at a structured database. I'll use the example of a contacts database, a place where we store people's names and their phone numbers. To find a person and their phone number in the database, some software code is run to search the database and return the correct result. Well-designed databases can search millions, even billions of records and return a result often in a fraction of a second. In a structured database, the data is stored in an organized and logical manner. Imagine for a moment columns and rows. In each row is a different person's first and last name and their phone number, with each distinct piece of data in its own column, respectively. We call this a database table, and because these items have a logical relationship between each other, we get the term relational database. Let's now look at an unstructured database. It's basically the opposite of a structured database in that no consistent and organized structure exists. Remarkably, most of the data collected today is in an unstructured format. Some say it's as high as between 80 to 90% of all data. Consider all the data that is collected and stored on social media platforms, in emails and other online documents. Unlike the predictability of a structured contact database with first name, last name, and phone number in rows and columns, these unstructured systems have to manage all manner of data. In Facebook, for example, posts can include various lengths and types of text, and include photos, videos, and music. Fortunately, a healthy ecosystem of providers has created tools for managing unstructured data really well. Both structured and unstructured databases are the foundation of almost all computing systems in place today. Whether it's the internal systems of an organization for, say, financial accounting or customer contact information, or for popular commercial services provided by your bank, Amazon, or Google, it's databases that store and manage all the content for each one of these. The databases I've described typically reside on a high-performance central computer with access to sizable storage. It may live in a data center at a business or at a third-party provider. Let's use these blocks to illustrate this design and then contrast it with another design. This block in the center represents a central server. These blocks that surround the server, we call them clients, and they access the data on the central server. This is client-server architecture. These clients can be laptop computers, smartphones, tablets, and other devices. What we're looking at here is a centralized architecture with all database management conducted in one place. Let's look at another design. Instead of a central server, these new blocks I'm placing in the center, the equivalent of different servers, are all going to contain all, part, or unique data that would have resided on just a single central architecture. Clients access data as normal, often unaware that the data is decentralized and distributed among systems. This design is more complex than a centralized system, but it does improve performance and has better support for failure. That's because a centralized system technically has a single point of failure. Finally, let's look at how client access is managed in these traditional database environments. In all instances, there are mechanisms for allowing certain people to have specific access privileges. One access type may enable a user to just look up information in the database, while another type may enable rights to add or delete data. In every instance where rights are granted to a user, there is an authority that provides those rights. A quick example may really help here. Imagine a university system that contains student grades. Professors can enter and change grades, but students can only view grades. A system administrator would assign and manage those access rights to professors and students. This simplified explanation of database security generally serves organizations well, but it has limitations. For example, what happens if someone who is not authorized obtains certain rights and gains access to a database? Depending on the access level, they can create, read, update, and delete records, causing all sorts of problems. It happens more often than we would like. Students, for example, shouldn't be able to change their grades. What you'll soon discover is that at its heart, a blockchain is a new type of database with a specific network architecture. It leverages the positive elements of a traditional database and reinvents other elements in order to overcome existing challenges. What will become clear as we continue in this course is that in redesigning these systems, blockchain creates a completely new platform for innovation. A core characteristic of a traditional database is that it typically has a central authority that governs it. All rights to the database are owned by the organization that creates it. They can decide who has access to it and what types of access they can actually have. They also decide, for example, what is stored in it, what is deleted, and what is archived. This design has at least two potential weaknesses to it. First, if a system relies on a central database, this can result in a single point of failure. If either the central authority is compromised, such as hackers getting administrator login names and passwords, or a backdoor is exposed, the database can be subject to all manner of risk. The second potential weakness is that all power is held by the central authority. Now, let's be clear, in computing, this has generally been a good thing. For example, if you run an e-commerce website, you probably want total control over it. You, as the central authority, perhaps as CEO or CTO, gets to decide all aspects of that environment, including shutting it down if that's what you decide. However, central authority often requires dedicated personnel with special skills. It also requires, depending on the type of system, many human checks and balances, such as complex approval workflows. These systems are sometimes prone to errors and access delays. Intuitively, this also means that humans remain the final arbiter of who has authority and whether a transaction is valid. We see this in most contract work. A contract between two entities completed over the internet still requires one or more central authority validators. For example, with a mortgage, banks must validate available funds and approve loans, title companies must validate properties, and legal professionals must be required to validate signatures and other legal requirements. Each of these independent and historically important central authorities has unique power that levies considerable overhead in a mortgage transaction. The transactions written to the relevant databases all take time to process. They also impose costs, are vulnerable to hacking, provide limited opportunity for participation from those impacted, require special skills, and can be error-prone. Up until now, we've had to accept these overheads and their costs. It's been this way because of, for example, the high human trust requirements of each transaction and many technological limitations. However, these overheads and limitations become the ideal solution targets for a blockchain system. The novelty of this technology means that software code can replace traditional human trust mechanisms. It also means that authority over decisions can be distributed across participants, resulting in the elimination of the risks and challenges of central power. Blockchain's design also improves security and the integrity of all types of transactions. These qualities give blockchain technology remarkable power in a wide range of applications. How it does this will be the subject of an upcoming video. But first, let's take a look at how Bitcoin, the popular cryptocurrency, gave birth to blockchain technology. Let's talk about the origin of blockchain. The fact that the blockchain emerges as the essential supporting mechanism for a new digital currency will play an important role in our understanding of this technology. The first mention of Bitcoin, a new form of electronic money, showed up in a proposal paper written by Satoshi Nakamoto in 2008. Turns out this was not a real person's name. Speculation is that it was a group of writers who used a pseudonym. However, to this day, the mystery is still unresolved. At the heart of this proposal was a solution to the double spend problem. We can all recognize this problem through how easy it is to make unlimited copies of digital items. If a digital currency can be simply copied at will, for obvious reasons, it's never going to be viable as money. Satoshi solved this double spend problem. I'll describe the basics of how later on. In 2009, the proposal for Bitcoin was built and became real as an open source software project. Open source software permits anyone to inspect, modify, and enhance it. This important decision has enabled thousands of other cryptocurrencies to be created from the original Bitcoin code. Bitcoin enabled a digital currency that could be used person to person without the need for any intermediaries. It was the opposite of all other forms of typical currency we're used to. Specifically, the currency was built to exist outside the banking system, completely independent and free of any government or regulator, and unconcerned with borders and other traditional financial system limitations. As a currency, Bitcoin does not exist in a physical form. There are no coins or paper notes. It's made of bits, ones and zeros, and resides and operates natively on computer devices and networks. When a transaction takes place, it is recorded in identical copies of a blockchain database that live on computers in a distributed network. These transactions are validated and stored through a set of innovative and unique blockchain processes, which I discuss later. Top of mind for those curious about Bitcoin is how it functions as a currency and how it acquires value. Traditional money, that which is backed and maintained by the government, we call it fiat currency, must meet 4 criteria to have function and value: supply, demand, utility, and trust. Supply and demand will typically determine value. Utility means it can be used to buy and sell products and services. And trust means having the confidence that it will actually store value and be accepted for transactions. Let's look at those dimensions as they relate to Bitcoin. When it was launched in 2009, a finite number of 21 million Bitcoins was established. These Bitcoins are introduced gradually for use via a process of mining, an important concept I'll explain later. As time passes, mining is becoming increasingly difficult and costly, much like harvesting silver, gold, and oil. Bitcoin therefore has limited supply, a cost to mine, and a demand that is relative to its market value, something determined by how much each person is prepared to pay for it. Now, can Bitcoin be used to buy anything? Well, absolutely. For example, all types of products and services can be purchased using it. This means it has utility. Finally, over the course of the past 10 years, Bitcoin has gained credibility as more people participate, greater uses have been adopted, and the technology has matured. Trust has been established. Bitcoin and the thousands of cryptocurrencies that have followed have succeeded beyond most people's expectations. They have stunned our global financial systems and perplexed governments and economists. They have become the basis for new innovation in organizations. Acknowledging the incredible achievement of Bitcoin, the underlying blockchain technology may be an even more surprising success story. Without Bitcoin, blockchain as we know it today would either have never emerged as it has, or would have come about later in a completely different way. In this way, we must recognize and give credit to Bitcoin, a project that introduced a viable cryptocurrency for giving birth to the version of blockchain we know today. In basic terms, a blockchain is a distributed database that manages and stores data. Its power and innovative qualities reside in containing some unique characteristics and novel processes. Let's explore those. First things first. With blockchain, there is no central database. There is no central control. Participants in a blockchain-based application, such as a cryptocurrency, interact with an identical copy of the supporting database that is distributed over many computers. We refer to these computers as nodes. In the early days of Bitcoin, it wasn't unusual for every user to have the entire supporting blockchain on their device. It's still the case today that many users of a blockchain-based system will store a full copy of the database because of an application requirement, or their role on the network, or their personal preference. Today, many blockchains, particularly cryptocurrencies, have evolved such that many users simply interact with a provider that hosts a copy of the relevant blockchain. Let's look at the steps of how a Bitcoin transaction is processed over the decentralized network. I'm going to use the example of Carlos sending Serena 1 Bitcoin as payment. Of course, we assume that Carlos has 1 or more Bitcoins already assigned to him. He may have purchased them using fiat currency such as US dollars, or someone may have paid him previously with Bitcoin. So let's begin. Carlos broadcasts his transaction request to the entire network. The transaction contains his intention to give 1 Bitcoin to Serena. The fact that all participants can see all transactions elevates integrity. After all, it's harder to cheat when everything is visible and everyone is watching. Next, a set of network participants, those with a special role called a miner, work to validate the transaction. It's this process that ultimately eliminates the double spend problem discussed earlier, and ensures a high degree of security in the system. If the miners reach consensus that the transaction is valid, it is approved and added to the identical blockchain databases on the network. If a node is offline, once it comes online, any new transactions will be automatically added to bring it up to date. Okay, that's the essential mechanics, but as you can imagine, there's a lot of detail still to unpack. First, all participants in the network have a set of keys, a public key and a private key. A public key is the equivalent of an address. When Carlos sends 1 Bitcoin to Serena, he specifies her public key as the destination for the money. The private key is used to uniquely sign any transaction that is broadcast. That means that when Carlos broadcasts his request, it's signed with his private key. What this looks like to others on the network is that there's a transaction signed with a unique private key directed to a public key. Since all transactions are typically inspectable by anyone, unless they've made it obvious, both Carlos and Serena are generally unknown to the rest of the network. You can think of these keys as the way transactions are assigned and how a person proves they are associated with and can access specific transactions. Next, let's briefly explore what miners do and why they do what they do. On a blockchain network, new transactions are being continuously broadcast by many participants. These transactions are approved in batches and added to the blockchain database. Let me show you with these blocks that I have here. When each batch or block of data is added, it is uniquely tied through mathematics to the previous block in the sequence or chain of blocks in the database. In this way, we get the term blockchain. This math means that fraudulently interfering with any previous block in the chain will fail, because all subsequent blocks, being dependent, will be computationally impossible and will reject the interference. This mathematical dependency is achieved by a math problem that miners spend considerable computing power and in turn electrical power to compete and solve. The process of work to solve the math problem and thus ensure that only valid blocks are added is called proof of work. It's proof that work was expended to approve transactions. Once the math problem is solved, it's broadcast to the other miners who quickly test it and agree. In other words, approval is by consensus. Why do miners bother to do this work? Because they are rewarded with Bitcoin for their efforts. That's their incentive. In a neat twist, this is also how new Bitcoin is introduced. Proof of work requires significant effort and ensures that only valid transactions are approved by consensus. This is a strong disincentive for bad behavior. In summary, blockchain achieves its trustless, secure architecture through network decentralization, transaction dependency, and proof of work. These 3 core dimensions were described in Satoshi's 2008 Bitcoin paper and proved to be the winning combination to enable a whole new way to manage transactions in a distributed ledger without a central authority. Even with the rapid growth of blockchain technology in a variety of applications and industries, cryptocurrency still dominates its use. However, beyond the use of cryptocurrency as a form of digital money, cryptos, short for cryptocurrency, and a derivative called crypto tokens, form the basis for some fascinating and important innovation. I'll begin with a quick overview of the current crypto market. Bitcoin was the first cryptocurrency and continues to be the largest and most impactful. Its success provided the basis for thousands of spin-off cryptocurrencies. We call these altcoins, short for alternative coins. Many are, in fact, based on the Bitcoin codebase, which being open source allows anyone to copy and modify the code. This makes it easy for literally anyone to create their own cryptocurrency. Some cryptos exist to compete with Bitcoin, but also to serve specific needs and applications. For example, cryptos are used to support cross-border payments, making it easier and faster to send money between 2 countries with different national currencies. Cryptos are also used as a mechanism for raising capital. While Bitcoin is the cryptocurrency leader both in terms of market capitalization and usage, The second most popular is a cryptocurrency called Ether. Ether runs on a blockchain platform called Ethereum, which supports both a crypto and a system for application development. Unlike Bitcoin, we know the actual person who created Ethereum. It was created in 2013 by a Russian Canadian called Vitalik Buterin. Ethereum uses the decentralized architecture of blockchain technology to turn its network into a computer. Each connected device collectively makes up the Ethereum Virtual Machine, or EVM. This EVM is low cost, scales massively, avoids downtime, and has security baked into all its functions. Solutions can be built using its proprietary programming language called Solidity. Examples of Ethereum applications called dApps include sophisticated banking services, marketplaces for digital art, crowdfunding, and games. Ethereum's crypto Ether is used as the funding mechanism for computational resources utilized on the network, and to pay any transaction fees required by dApps. Another type of cryptocurrency that runs on a blockchain is called a crypto token. Cryptos, sometimes referred to as crypto coins, are the equivalent of cash, but crypto tokens can be used to represent many other types of value. Two popular forms of crypto tokens are security tokens and utility tokens. Security tokens can be used to represent whole or fractional ownership of any asset that already has value, such as real estate, a car, or corporate stock. For example, a person could own a token that represents a 5% share of a boat. Utility tokens give users access to a future product or service. For example, a startup issues utility tokens to users to raise money, and later users utilize the tokens to use the startup service. The crypto coin and token space continue to introduce new concepts and innovation at a rapid rate. As time passes, the technology becomes more mature and confidence in use increases. That said, it is still a risky domain from the perspectives of stability, reliability, and market acceptance. The unique nature of cryptocurrency, which largely operates outside the confines of existing financial systems and local and international regulations, is presenting challenges to governments and regulators. Some countries are embracing cryptocurrencies, while others are banning them. It's also easy for me to focus on the positives of crypto, of which there are many. But it's important to recognize that it is also used for nefarious uses, such as ransomware and buying and selling contraband on the dark web. Cryptos will continue to represent a massive use case for blockchain technology for the foreseeable future, as other valuable uses also emerge. Whatever your journey looks like in the blockchain space, expect cryptos to play a key role.
To participate in a blockchain network requires the use of keys. These are fixed-length sequences of unique numbers and letters like you see here. These keys not only enable you to access a blockchain network, but they are essential in how transactions are validated, authenticated, stored, and managed. Understanding the basics of what keys are and how they are created is important in appreciating how blockchain-based systems work. Since blockchain networks are decentralized, there is no central authentication mechanism. This means there is no system to log into, such that a typical login name and password that we're all familiar with is useless. In addition, public blockchains are what's called permissionless, meaning that user credentials are not required. Blockchains don't care who you are as long as you possess something unique that associates you as the owner, the sender, or receiver of a transaction. The unique item you possess is a minimum of one key pair. The pair is made up of a public key and a private key. They're a pair because the public key is mathematically generated from the private key, and they exclusively work together. A public key, as its name suggests, can be viewable and accessed by anyone. In fact, in blockchain, your public key is the address that transactions will be sent to. For example, if someone wants to pay you with cryptocurrency, you'll provide them with your public key. Conversely, a private key must be kept private, as anyone in possession of it can gain access to transactions associated with it. When transmitting a transaction on a blockchain network, the private key is used to create a digital signature that is embedded in the transaction. Only someone with the private key can later prove ownership over it. Finally, keys are stored in wallets. Wallets can take many forms, including software and hardware, and they can also be hosted by third parties, such as a cryptocurrency exchange. Your wallet tells you what transactions are associated with your keys. Wallets don't store crypto, for example, they just report on the amount and type of crypto owned, which is derived from the keys in the wallet. By using keys, blockchain's trustless architecture enables anyone to participate. Uniquely, keys provide a robust way to send and receive transactions, as well as prove transaction ownership without the need for intermediaries. Before I discuss how they're used, let's take a look at how key pairs are created. There are many ways to generate keys. It depends on the type of security desired and the requirements of the blockchain system. For example, Bitcoin uses the elliptic curve digital signature algorithm, or ECDSA. For most users, keys will be created by third-party software or a provider, but anyone can create keys, as I will demonstrate here. For the purposes of this demo and for simplicity, I'm using an RSA key generator. I first choose the level of security. I'm going to use the default key length of 1024. You'll see that there are options for 2048 and 4096 too. The longer the key, the more secure it is. Now I simply click on Generate Key Pair and you will see the results generated here. The public key on the right has been derived from the private key on the left. Each of the keys are a series of unique letters and numbers, as you can see. Given the stunning number of combinations, it's unlikely this key pair already exists, and so these can now be copied and used.
It's not unreasonable to believe that blockchain is primarily a mechanism to support cryptocurrencies. For sure, crypto coins and crypto tokens represent a big proportion of its current use. It's also important to acknowledge that it's often these cryptos that power the new innovation that blockchain is enabling. For example, the Ethereum blockchain uses its own cryptocurrency, Ether, as a mechanism for user fees that power everything from games to managing digital assets. After Bitcoin was launched in 2009, blockchain technology began to be recognized as a platform for a wide range of uses beyond cryptocurrency. As the technology has matured, and in order to support new, complex implementations, a large blockchain ecosystem has emerged. Until now, I've only discussed blockchains that are permissionless and public. These open architectures allow anyone to participate. Since it's decentralized and without authority, there's no approval process. Everyone can join a permissionless blockchain. For proponents of the technology, this is a central strength. That said, there's now a sizable market for blockchain uses where approval for participation is required, and access levels and roles are controlled. These are called permissioned or private blockchains, and are often used within and between private enterprises. A popular private blockchain is called Hyperledger. Sure, it's counterintuitive because the spirit and value of blockchain represents the opposite of these needs. However, the value of certain aspects of blockchain, such as immutability, where only transactions are written and never deleted, is being applied in a private blockchain context. Another example, such as a document workflow process between enterprises that must be kept confidential, might be considered a candidate for a private blockchain. Blockchain technology has many qualities such as processing efficiencies, lower costs for transactions, transparency, traceability, that is, being able to analyze the entire history of records, and a high degree of security and integrity. These qualities lend themselves to supporting a wide range of industries and applications. The financial sector is continuing to see the steady adoption of blockchain technology in support of their services and innovation efforts. But in fairness, while real production solutions do exist, a large number of financial applications have existed in an experimental mode. That's changing now, and it's anticipated that in the next few years, many of these experiments will convert to production systems. We're also beginning to see the emergence of an entire financial ecosystem based solely on blockchain technology called decentralized finance, or DeFi. DeFi startups offer a range of popular services from lending to insurance, and also have the potential to be highly disruptive. With so many cryptos or altcoins, an ecosystem of organizations and services to enable more people to buy and sell cryptos has emerged. Called exchanges, these services are the equivalent of a blockchain banking system that supports capabilities such as the storage of cryptos, user keys to be specific, currency conversion from altcoin to altcoin, and also from crypto to fiat currency, and vice versa, and also market analytics. Some traditional banks are now beginning to offer similar services. Recently, a specific type of crypto token, a non-fungible token or NFT, has been used to support a new ecosystem for people who want to collect and trade in digital assets. It has also created a growing platform for digital artists to market and auction their products. Similar to the popularity of items such as physical baseball cards, collectors can buy and sell digital images, videos, and other unique digital assets. Between the years 2017 and 2020, the NFT market grew over 700%, and by early 2021 was worth well over $300 million. Blockchain technology benefits are also demonstrated in other areas such as support for supply chain management, identity management, and in the authentication of a wide range of credentials such as degrees, certificates, and licenses. Each of these areas is generating new providers and enabling opportunities for existing vendors to diversify into servicing emerging requirements. What's clear is that blockchain is now creating opportunity across the economy in surprising ways. Its growing maturity and adoption is building credibility and ensuring that it becomes an important tool in the array of technologies ready to support our future needs. There's no shortage of speculation about how blockchains may be used in the future. So instead, let's look at actual blockchain uses today. Everledger is a platform that illuminates transparency in a number of industries. Specifically, the solution manages characteristics of assets that include origin, sustainability footprint, and compliance standards. It can be used to bring new insights to the life cycle of items such as art, batteries, diamonds, and luxury goods. The platform works by storing an authenticated digital record, a digital twin, of an asset in a blockchain. This record contains details on how it came to be, where it came from, and who made it. As the asset moves through the life cycle, all details are recorded on the Everledger blockchain. Because of provenance, meaning the record of something's origination, and with immutability, that no record is ever deleted, all manner of stakeholders can have greater confidence in the details of an asset. This solution helps in understanding whether, for example, diamonds came from mines with ethical standards, that batteries don't use banned chemicals, and whether luxury goods are counterfeit or stolen. Let's look at another fascinating real use of blockchain today. Most organizations in the world today are formed around a hierarchy. There are leaders and subordinates, all with specific roles and responsibilities. But what if we could organize differently? For example, in a way that would eliminate hierarchy and where decisions are made autonomously and by participants that don't need to know each other. This is the nature of a decentralized autonomous organization, or DAO. It's built and operated on blockchain technology. The value of a DAO includes eliminating the need to trust participants, since trust is encoded in the software, not people. It's a mechanism for human coordination and can be global on day one. DAOs have an entirely democratic design, as everyone has equal opportunities to participate and anyone can submit ideas for innovation or have their voice heard around an organizational decision. In addition, I'm guessing there are many people who would be happy not to have anyone to report to. DAOs don't have managers. Many of the DAOs that exist today are in the financial sector. Using blockchain technology means there's no need for any financial intermediaries. All financial transactions and rules are recorded in the blockchain system, and security and integrity, despite the distributed nature of the organization, is strongly maintained. A popular example of a DAO is the Bitcoin network. DAOs are certainly in their early stages, and there have been notable challenges. With growing evidence of success, they may be here to stay. Whether they grow significantly beyond their current scope is yet to be seen. Finally, let's look at blockchain as a solution for online voting. There continues to be significant underlying challenges with having broadly accepted online voting solutions. Cited most frequently are the issues with ensuring that a person is who they say they are, that they can only vote once for a given election, and that everyone's vote is protected from meddling. These areas are not trivial to solve. Even with the technological hurdles overcome, we'll still need to convince people that online voting is safe and that they should have confidence in the integrity of their online vote. Let's look at a case study. The Rock and Roll Hall of Fame and Museum, located in Cleveland, Ohio, is a famous and popular organization for education and inspiring visitors on the power of rock music. Each year, the organization inducts new musicians into their Hall of Fame through votes cast by its members. In 2016, when the vote was cast using a traditional online voting application, a computer bot attacked the results and produced erroneous results. Great embarrassment ensued, and there was damage to the organization's credibility. The following year, for the inductee vote, a blockchain solution from a company called Votum was used. It successfully processed over 1.8 million votes from over 100 different countries without issue. At the time, it was the largest use of online voting using blockchain. The system was secure, auditable, tamper-proof, and low cost. Of course, citing one successful case study doesn't suggest blockchain will ultimately be the answer to all online voting needs. For sure, voting within an organization is less challenging than what's required in large-scale public office elections. There's an ongoing and rigorous debate about whether blockchain will succeed in that context. Regardless, it's likely blockchain-based online voting will grow in the years ahead. These examples demonstrate both the increasing diversity of blockchain technology uses and that it's solving real challenges today. As a problem solver and a creator of innovation, blockchain appears to have a great future ahead. Blockchain technology is a work in progress. Not only does the underlying technology continue to evolve and mature, but its features and applications are expanding rapidly. By far, the most compelling and established uses of blockchain continue to be cryptocurrencies and solutions within the financial industry. But other innovative uses are emerging. What's making blockchain particularly valuable is its use as a development platform. The leader in this area is Ethereum, a blockchain I mentioned earlier that has a cryptocurrency called Ether and a fully fledged decentralized programmable environment. The term smart contract is used to describe code that runs on a blockchain. A smart contract is a series of functions that execute when certain conditions are met. Unlike traditional contracts, execution does not rely on, for example, legal language interpretation or the promptness and discretion of humans. Rather, smart contracts run predictably and accurately. An example of a smart contract in a supply chain would be the automatic confirmation of payment for goods once delivered and the subsequent update of a stock inventory. But consider the role of smart contracts in improving the accuracy and efficiency of thousands of common processes in real estate, finance, healthcare, law firms, factories, and government. Let's take a look at the important role of smart contracts in the buying and selling of digital assets. Today, a growth area for blockchain technology is the ability to manage the authenticity and ownership of digital goods, such as photos and art. Using non-fungible tokens or NFTs, these crypto tokens store details such as the owner and a description of the digital asset on a blockchain. If the owner decides to sell the NFT, it will be transferred to a buyer using a smart contract. The transaction will certify the new owner, transfer any monies due, and conclude the sale without any loose ends. All parties can be confident that the new owner details and monetary exchange will be confidently settled. The rise of NFTs is notable, for example, in the collector space, but also in any industry that wants confidence in the authenticity of digital and even non-digital assets. NFTs are not without naysayers who maintain that they're a novelty and won't be sustained over the long term. In any case, we'll all find out soon enough. Programmable blockchains, and in particular Ethereum and its smart contracts, are powering a completely new set of financial products and services. Unlike the complexities of the traditional banking ecosystem that have many requirements and are not available to everyone, decentralized finance, or DeFi, only requires an internet connection. DeFi services are global and open 24/7. There's no central authority to block use, deny services, or require pre-qualified individuals. Transactions are fast and free of human error. Remember, it's the code that runs and validates the processes, not the behavior of humans. I've provided many examples of all the benefits of an open, transparent, and public blockchain. That said, many of the qualities of blockchain technology, such as provenance, immutability, security, compliance, and smart contracts, are also attractive to enterprises. However, for their needs, they require a more managed environment. Sure, it's counterintuitive in many ways to the core spirit of blockchain technology, but still it offers enough value for a private permissioned blockchain to make sense. A number of vendors are providing private blockchains and solutions, including Hyperledger Fabric and IBM Blockchain. A rapidly emerging blockchain innovation for enterprises is BaaS, or Blockchain as a Service. This uses a cloud-based architecture to enable the rapid development of blockchain solutions. It's based on the increasingly popular use of Software as a Service, or SaaS, and provides all capabilities on demand over the internet. In addition to quickly creating solutions, BaaS keeps maintenance low and provides easier access to state-of-the-art blockchain functions. Organizations can quickly build and deploy blockchain apps. Providers such as Microsoft and Kaledo are offering full-service BaaS solutions. Assuming BaaS takes off, and the evidence suggests it will, this will likely result in the broader adoption of blockchain. There's little doubt that blockchain innovation continues at a rapid pace. The examples in this video illustrate how the technology is growing and broadening its value. It will be fascinating to see what it becomes and the value it will provide in the years ahead. The present and future promise of blockchain technology has captivated a sizable community of global enthusiasts and advocates. The unique qualities of the software to solve difficult and complex issues, the innovative applications being deployed, and its legions of users reflect the value that blockchain has already brought to the table. In the last couple of years, business leaders have moved from a wait-and-see approach to recognizing that they must move forward and invest in blockchain efforts to support their operational and market strategies. Despite this optimism, executives still point to some valid uncertainties and challenges that are muting broad and rapid adoption. In a recent survey of 600 executives by the global consulting firm PwC, a significant percentage of respondents said their organizations had some form of involvement in blockchain technology. Let's break down the numbers. Within these organizations, 14% had no projects underway, 20% were in the research phase, and 7% were paused in their efforts. Together, this represents already 41% of organizations. 30% were in some phase of developing a project, 10% were piloting, and finally, only 15% were live with the project. While this data isn't too bad, and I'd argue it's quite encouraging, it's also indicative of some hesitancy. The PwC survey identified a number of barriers to adoption. Those barriers included regulatory uncertainty, lack of trust among users, interoperability limitations, and scalability issues. A similar survey conducted by global consulting firm Deloitte of 1,500 senior executives identified 3 top reasons for hesitant adoption of blockchain technology: the challenges of implementation, particularly related to integration or replacement of existing systems, regulatory issues, and finally, fear of security threats. A theme that runs throughout blockchain adoption hesitancy is a lack of trust in the technology. It's painfully ironic because trust is at the core of blockchain's true unique value. So what are these trust issues and concerns of business leaders? One obvious concern is that the technology is still emerging. As with all new technology, there are doubts about stability, reliability, scalability, and security. Leaders comfortable with older, tried and tested methods can be concerned about moving important processes to a new platform. They are worried about the absence of regulations and laws and what that might mean for potential legal exposure. These are not irrational concerns. Despite blockchain's claim of being reliable and tamper-proof, there have been notable failures and breaches, including sizable thefts of cryptocurrencies from big name exchanges. Blockchain technology also continues to lack standardization, such as interoperability with other blockchains. It's good news, though, that progress is being made in this area. Perhaps the area contributing the greatest towards the gap in trust is a lack of understanding at the senior decision level about what blockchain is and what value it can bring. For too many, blockchain means cryptocurrency, and more often than not, specifically Bitcoin. To be fair, explaining blockchain isn't easy, and with limited time and patience, many business leaders haven't made it a priority to deeply appreciate the possibilities that technology can bring to their enterprise. Doubts and reservations about new technology are not new and can often be viewed as a positive. These are forcing functions that can help to ensure weaknesses are addressed and trust issues are overcome. As Kevin Kelly notes in his 2016 book, The Inevitable, when executives were first introduced to the promise of the internet in the 1990s, many discounted it. They said that consumers would never trust it for buying products or for meeting their banking needs. Many thought that content would remain the domain of powerful media companies. Many leaders could not see the disruption that was to come. Sometimes it feels this way with blockchain technology. It has massive potential, and the leaders and organizations that are ready to invest now will most likely reap the early rewards. After several years of taking a conservative approach to blockchain technology use in the enterprise, business executives are turning a corner. Despite a number of valid reservations that I discussed in detail previously, leaders to varying degrees are ready to invest in blockchain experiments, prototypes, pilots, and even develop and deploy production solutions. They recognize that the technology may be required due to demands from the marketplace. For example, if you're a bank, you've got to decide whether you're going to support cryptocurrencies or not. Leaders also see a lot of value in the unique qualities of blockchain technology to enhance their internal processes and to deliver better services to their customers. Now that organizations are moving forward, they've still got some hurdles to overcome. One glaring challenge is ensuring the right skills are available. Of course, many businesses will engage a third-party business to assist, but there's a lot of value in having full-time staff to lead and maintain efforts. The availability of qualified talent is in short supply. It's a great market for people with expert skills in blockchain technology, but it's a challenge for internal recruiters who are tasked with sourcing the best talent. Organizations may find it beneficial to train existing staff by investing in their skills development. This can be an excellent route to take as it demonstrates an organization's willingness to invest in their own people. There are a growing number of avenues to acquire skills as the training marketplace for blockchain heats up. My related courses and other instructor offerings on LinkedIn Learning are excellent resources too. Organizations will need to recognize that the advantages of blockchain may result in making some of their services and market value obsolete. While this is a feature of a lot of innovation and should drive a business to anticipate market and technological driven change and evolve accordingly, it can, in the short term, be a source of significant anxiety. For example, if an organization demonstrates value through forms of intermediary services, blockchain solutions can make those intermediaries obsolete. Peer-to-peer and smart contract-driven processes means skipping human-based facilitation services. Some new technology-focused mortgage offerings already demonstrate that many human services are no longer required in their value chain. When blockchain solutions are being adopted, plugging the technology into an existing environment still has a high level of complexity and risk associated with it. For example, a decentralized proof-of-work system may need to coexist and interact with one or more centralized multi-tier systems, both inside and outside an organization. It may also need to work with other blockchain systems that aren't yet standardized for interoperability. It's not impossible, of course, but it's certainly not easy, and there are risks in relying on these heterogeneous environments to provide the kind of reliability we've come to expect in centralized tech. Arguably, we have no choice. Contemporary information technology architecture is almost heterogeneous by definition. An enterprise taking the positive leap into blockchain territory will do so knowing that there are still insufficient regulations, many trust and privacy challenges, and a lot of risk in both the maturity of the technology and the cybersecurity vulnerabilities. These are not showstoppers, but they will shape how an enterprise might think about the blockchain solutions it pursues. Perhaps the greatest risk is doing nothing. For an enterprise, this is always a choice. Faced with an array of legitimate concerns and a technology still emerging, it could be tempting to kick the can down the road. The spirit and intent to pursue blockchain may exist, but the commitment to invest and take some balanced risks may not. Some industries will be able to delay their efforts, or perhaps continue to just remain in the experimental phase of blockchain exploration for some time. But others, such as those in the financial sector, supply chain, government, healthcare, the Internet of Things space, and many more, will find that delaying their efforts or only proceeding tentatively may backfire badly. Today, in the opening decades of the 21st century, taking risks, embracing uncertainty, and making bets on where the market is going is just the nature of business. Those that are agile, that make informed choices, and get a bit of luck along the way may well reap the biggest rewards. In 2009, a new digital currency called Bitcoin was born on the internet. It delivered the ability for payments to be made confidently, directly between any parties, without intermediaries, central authority, and government oversight. Its success has expanded the realm of the possible and reinforced the notion that digital innovation has the power to continually surprise and disrupt. The ultimate long-term implications of Bitcoin and all the cryptocurrencies that have followed is still a story to be told. No doubt, there will be many twists and turns along the way, just as there have been so far. What we do know is that the core technology that has powered Bitcoin from day one, the underlying distributed ledger called blockchain, has emerged as its own force, with the potential to be even more impactful and disruptive than the life it gave to cryptocurrency. Despite its existing challenges and some adoption hesitancy, which continues to shrink, blockchain innovation is growing its capabilities and increasing its value. The impact of blockchain technology is being experienced across many industries, ranging from finance to supply chain and from gaming to government. Given the current trajectory of blockchain adoption and its expanding value, its most important and remarkable days are ahead. This course has provided you with a basic introduction to blockchain technology. I covered what it is, how it works, and the challenges and risks associated with it. However, there's a lot more to know, and I hope I've inspired you to continue your blockchain learning path. What should you do next? Well, LinkedIn Learning offers many courses on blockchain and cryptocurrencies, including many that I've created for you. I suggest taking blockchain beyond the basics next. That will go into a lot more technical detail and elaborate on many of the concepts this course summarized at a high level. After that, I suggest taking my Cryptocurrency Foundations course. Beyond that, you can take a look at securing cryptocurrencies and my course on non-fungible tokens or NFTs. You'll also find excellent courses from other instructors on Bitcoin, Ethereum, Solidity, which is Ethereum's programming language, and much more. Blockchain and its associated ecosystem of technologies and required skills will provide opportunities for organizations and great career options for individuals like you. I'm excited about the seemingly endless possibilities of blockchain. I hope you are too. Good luck, and thank you for learning with me.